In crystal field theory, the interaction between the d orbitals of a central metal ion and the surrounding ligands lead to the splitting of these orbitals into distinct energy levels. So here we can see our d orbitals that have been split due to the ligands and their ability to have their own electric and magnetic fields as they come towards the d orbitals, causing them to split into a higher energy and a lower energy. So the three lower energies are going to be the T2G orbitals, and the two higher energies or elevated energies are going to be the EG orbitals. Now we know that there's going to be a splitting energy as you go from the lower to the higher, and basically that is going to be our delta energy here. So we can write delta, we can write delta O, or delta octahedral, because this is going to be the splitting energy for the octahedral geometry. Now, this splitting energy depends on the arrangement and nature of ligands, like I was saying before, especially their ability to influence the electron distribution and the d orbitals themselves. It also is going to depend on oxidation state, which we will get into later. Now, the color of a complex ion is going to depend on the wavelength of light that it absorbs or transmits based on how small or large this splitting energy is. Okay, folks? So you might be asking, what light are we talking about? For that, we are going to have to go back to the electromagnetic spectrum from 101 and focus on the visible light spectrum that we see here. And visible light means what we can see with the human eye, and it's based on Roy G. Biv. So that's how I kind of always learned it. And that is basically listing out colors. R is going to be for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, and V for violet. Okay? And as you can see, they all have different wavelengths. Let me just make sure I erase that portion. So from the visible light spectrum, as you can see, each of our Roy G. Bivs here, or our different colors, have a different wavelength attached to them. So for example, if you were going with red, then you were looking at something that's around the 650 nanometers. Blue would be around 450 nanometers, for example. But you also can have a blend of colors, like our yellow-green here, which can have 570 nanometers. So it's all different size wavelength. Now the question becomes, am I responsible to know each wavelength? Well, no. But you can know trends based on this spectrum. So as you can see, we do have increasing wavelength as you go this way, increasing energy as you go that way. And these small trends you can start learning about to help you basically remember this portion of the information. So let's talk about some trends we see. So for example, with the color red here, one trend we see is that when you're with the red or the oranges or the yellows, they tend to have longer wavelengths. So you're going to have longer wavelengths. You have longer wavelengths. You're also going to have basically lower energy, okay? So if you have longer wavelengths, you have lower energy. That means if you have vice versa, shorter wavelengths, you're going to have higher energy. What do we mean by energy? It means that the photon of light that's going to come from violet, which has a shorter wavelength of 400 nanometers, is going to be way higher in energy than if you have a photon of light with the color red attached to it that has a longer wavelength with 700 nanometers. And where did these trends come from? Of course, again, it's going to be the relationship of energy and wavelength. You have energy is going to equal to Planck's constant, speed of light, and then, of course, wavelength. So as you can see, we do have an inverse relationship between energy and wavelength. So when you decrease or you shorten the wavelength, which we see here, you're going to increase energy. And the trend that we see here is when you have a longer wavelength, you're also going to decrease energy. So that is where we get these trends from, which allow us to kind of make the predictions we need and continue on with crystal field theory. We can also see our good old Roy, let me get a different color, sorry folks. We can also see our good old Roy G. Biv here in a color wheel. So if you observe a certain color, so say we absorb violet here, okay, you would transmit or reflect its complement. So since I'm absorbing one single violet here, I'm going to absorb the violet, and I'm going to reflect its complement color, which would be the yellow here. I can also say, what if I absorbed our green color here? That means I would actually reflect or transmit red. And you can do that with any kind of complement color that you see here, even with some of the blended colors as well. And so when you see our Roy G. Biv inside of this color wheel, it just makes it easier for us to get those complements, as we will see when we get into examples later on. So how does this specifically apply to complex ions? Well, folks, we're back to our d orbitals. We know we have our higher energy d orbitals and our lower energy d orbitals. So let's go ahead and say we have an electron. This electron is now going to absorb energy and move to a higher energy level. that energy that it absorbs is going to be related to the splitting energy between these d orbitals here. Okay, folks? So the difference between these two energy levels are going to represent the difference between these two energy levels, or our splitting energy, is going to represent a specific wavelength or wavelengths that have been absorbed by this particular electron here, moving from a lower energy to a higher energy. Okay? And so whatever remaining wavelengths are left over, they're going to be the ones that are transmitted or reflected. Of course, we also can say the complement colors will be the ones that are going to be perceived to us. So we know the energy difference between the d orbitals often allow photons in the visible range to be absorbed as electrons that go from lower energy d orbitals to higher. So if we have an electron here, it's going to be promoted to a higher energy level, and that splitting energy is going to allow certain wavelengths to be absorbed, and whatever wavelength is absorbed, and whatever wavelength is not absorbed, is going to be usually transmitted or reflected in solution to us, meaning what we can see with our eyes, right? So I just want to kind of get into some different ways we see color, just so that we're super clear on how color is going to be influenced in these complex ions. In general, we'll start off here. If an object is black, as we can see here, it's going to have the ability to absorb all colors of light. But of course, it doesn't reflect any colors. We just see it as black. So that one we can get through with. And then in contrast, if we have an object that is going to be white, it's going to reflect all colors, and it's going to also absorb those colors and reflect all those colors if the object is white. Now, let's talk about down here, which is what we see with a lot of different complexes, because a lot of times we see them as different colors versus white and black. So let's get into an example of what some electrons can do in d orbital. Let's start with this one first. So first, we can have an electron that's in a d orbital and is going to be promoted to a higher energy level. So it's going to go to the Eg energy levels from the lower T2G energy level. Now, if we have a situation where that electron is going to absorb every color except one, so let's just say it absorbs every color except the yellow color. That means the color that it will reflect would be yellow, because that's the only one it didn't absorb, right? So we can have a situation like that. Or we can have a situation that we normally talk about, which is in connection to the color wheel, which is that we're going to have the absorption of one photon of color. And of course, the reflection is going to be what we actually it's going to be the complement of that color. So again, we have this yellow object that we are seeing. And so that means since we are reflecting this yellow object, which will be in this color here, the absorbed color had to be the complement of it, which would be purple. So as you can see, or like blue or indigo. So it's this blue color here that's absorbed, which is why we can see this yellow object color here. So that is how we can see it in the complement form. Again, this yellow object here is only going to be yellow because it was able to absorb all other colors except this yellow one. And so that's what we see yellow here. I just want to make sure I cleared that up. So mainly for us, we're always going to be thinking of a lot of complements in our examples. So we're going to have you absorb one color. So say you absorb this color here. That means you're going to reflect its complement. And that's kind of how we understand it. You can also have situations where you have complex ions like this copper NH342+ in solution. And so when you have a solution, you're going to have a solvent and you're going to have a solute. So sometimes the solvents can also influence color because they have the ability to have solvent interactions, polarity, disturb the ligands, all kind of things. So you can end up seeing that you can have different types of charge changes and everything from just having a solvent outside of ligands and oxidation state being the only thing that influence color. So here, for example, we have all of our colors lined up. We already know that we have this blue color is what we see. Okay, that is what we see, meaning that is what is reflected. Now, as you can see, we're seeing a blue color here. And so we had to have this red-orange that would end up being absorbed so that we can see the blue color, which is going to be reflected of higher energy. And so again, you can go ahead and look at the color wheel and say, let me go ahead and find this red-orange color here, this red-orange. That was not really enough, okay? So say it's like this red-orange color, and of course the complement would be the blue color that relates to this color here. Okay, folks? So that's what we're looking at. Now, according to crystal field theory, the extent of the energy of this splitting here, so all this splitting, the extent of this splitting right here of these d orbitals are going to result in coloration that we know is going to be influenced by many things. So as we can see, it can be influenced by ligands, oxidation state, and now, like we just talked about, solvent. So we will see a small example of solvent here, but that's pretty much all we'll go through for this course. Let's go ahead and get into oxidation next. So we know that in coordination complexes, ligands create an electrostatic field that splits the d orbitals, of course, into higher energy levels and lower energy levels, creating a energy splitting or splitting energy that we call the crystal field splitting, right? And this is all going to be based on ligands, oxidation state, and all. We also saw a little example of solvent. So when a complex ion absorbs a photon of light energy, okay, when that electron goes from a low energy state up into a higher energy state, it's going to be based on this splitting energy that we see here. And so if it's a very large splitting energy, it's going to have the ability to absorb higher energy color. And of course, if it's very low energy or a small crystal field splitting, then it's going to have the ability to absorb, of course, low energy colors. So this crystal field splitting here, if it's going to be large or if it's going to be small, it has the ability to absorb, of course, small amounts of energy, low energy, and this is going to absorb high energy. What do we mean by low and high energy? We're talking about colors, right? Based on the electromagnetic spectrum. So we might be asking ourselves, well, why does oxidation state matter when it comes to color? Well, higher oxidation states means more loss of electrons, which means fewer electrons in these d orbitals here. So when you have less electrons in the d orbitals, what is that also going to mean? It means that you're going to have more of a positive energy. So for example, if I have Mn2 plus versus Mn7 plus, this is going to have way more positive energy as a central metal ion than the manganese 2 plus. So more positive energy means that there's going to be more attraction with those ligands. But we also remember that when ligands start attracting to the d orbitals, they repel. And due to that repulsion, they cause this splitting. So if you're super positive and you're getting more and more positive with higher oxidation numbers, you're going to want to attract more ligands, causing more repulsion, which then is going to mean more splitting, which means that you're going to have a larger splitting energy here, okay? And as we said before, when you have a larger splitting energy, you have the ability to start absorbing higher energy wavelengths like our violets, our indigos, and our blues on the Roy G. Biv or visible light spectrum. So let's go ahead and get into an example. Here we have a purple solution, and here we have a yellow solution, and it's based off of the different oxidation states of an element vanadium. So we have our complex ions. We have vanadium, H2O6, 2 plus. So the oxidation state of vanadium is simply 2 plus because H2O is 0 in monodentate. H2O is 0 in monodentate here as well, meaning neutral. So the vanadium is going to be 3 plus here. So first thing you have to ask yourself, okay, what color am I seeing? So the color you see is going to be the color that is going to be reflected / transmitted. And you are going to be seeing purple here. So if you want to figure out what is going to be absorbed, you just get the complement. If I'm seeing purple, say I'm seeing this purple here, the complement would be a yellow color. That means in order for me to be able to see this color here for vanadium 2 plus, this vanadium 2 plus would have had to absorb a low energy color like yellow in order to reflect a high energy color like purple, right? We can do the same thing for vanadium 3 plus. As we can see, we are looking at a yellow solution. So that means it had to have absorbed, go ahead and get a different color here. It absorbed a high energy color so that it can reflect this low energy color. All right, folks? So we just got to make sure that we're kind of just looking at how that just simple oxidation state change, the fact that it changes the splitting field energy is therefore going to change the color of the complexes as well. Okay? So again, so far, we've seen that crystal field theory talks about the splitting of these d orbitals, which are going to dictate color, which are going to depend on the solvent, the oxidation state like we just saw, and now ligands. And so let's go ahead and focus on those ligands.